Okay, so we'll finish up hypothesis testing, work through a few more examples today. I'll show you a little bit of work in Excel, if that kind of helps some people kind of be able to visualize it better. So we'll get some of that in today as well. So we left off, we kind of worked through this example. It was kind of a ridiculous one where we had a test statistic that actually supported the null. So we said, we didn't have to go through all the steps, but we could, and would kind of lead us to, see that if we find something that supports the null, we actually end up, failing to reject it. That makes sense. So let's, do one that makes it's a little bit more difficult. So let's say, I believe the original slides, I kind of had this phrase a little bit differently. So I changed it to be the way that I would kind of write it on the exam. And I'll talk about that kind of at the end of class. So let's say we want to test for whether or not more than 15% of Indiana mothers smoke while pregnant. Let's get this switched over to the dot cam. And we'll kind of start working along here. I think this is going to mess up us in class, or mess us up in class. We'll see. There we go. So we want to test for whether or not more than 15% of Indiana mothers smoke while pregnant. So what we want to test for, that's our alternative hypothesis. So we want to know, is this true population proportion more than 15% or a proportion of 0.15? We'll assume the exact opposite is true, which is that it's less than or equal to 0.15. Okay. So that's how we identify the null and alternative hypothesis. Whatever we're trying to test for, whatever we're trying to find, that's going to be our alternative hypothesis. The exact opposite is what we'll assume to be true, or the null. So here we've got a greater than sign in the null, or sorry, in the alternative hypothesis. So we have a, I guess, greater than or a right-tailed test. Right? We then were told, kind of, I think I originally had it up here, I gave you directly the sample proportion. Something I could ask you to do on the exam is, if I told you that 72 of your 400 mothers in your sample smoked while pregnant, well, what's that sample proportion? That would just be 72 over 400, which works out here to be 0.18. And our sample was of size 400, so we've got our sample size. Okay. So that's everything just kind of taken that we were given, and then also identifying our null and alternative hypothesis, and that we have a right-tailed test. Okay. So the next question is something like, what's the critical value? So what we're going to do is, for our critical values, we're looking at that standard normal distribution. And what we're trying to find is, what are the cutoff values that would give us kind of different alphas in the tail. So I think we had 3 here, 0.1, 0.05, and 0.01. So we've got a right-tailed test. So right away, what do I know should be true about the critical values? Should be positive, right? They're on the right side of this distribution, and this distribution is standard normal, so it's got a mean of 0. So we're going to be looking for the z value, or our critical value, that gives us 0.1 in that tail. Or said differently, kind of the 10% significance level. So what would give us kind of that alpha of 0.1 in my tail? So how do I find this? Well, got 2 different ways. So if I just simply look up alpha, right? Remember, the table always looks at the area in the left tail. So if I just look up alpha, it's actually going to be giving me the critical value that's over here, or sorry, not critical value, sorry, a z value that's over here on the left side, which will be negative. However, since this is a symmetric distribution, whatever value would give me 0.1 in the left tail, that same value but positive would give me 0.1 or alpha in the right tail. So I can look up in my table, z table, can try to find 0.1. It's going to be, oh, I went too far. Somewhere, so yeah, right here in between these two. So negative 1.28 or negative 1.29. We'll take the higher of the two. But remember, this is looking at kind of that left side. For a right-tailed test, I want alpha in the right tail of my distribution. So instead of negative 1.29, it'd be positive 1.29. Now, the other way I could have done this is said, okay, I know if I want 0.1 in the upper right tail, what area would be to the left of that value? Well, area under the curve is 1, so 0.9, right? Now, if I use my standard normal table to look up 0.9, I'm in between these two values. So 1.28 and 1.29, I found the same value, right? So there's kind of two different ways of finding that critical value for a right-tailed test, because if I use the principle of the fact that this is a symmetric distribution, I can simply look alpha up and just remember, oh yeah, that's the value, but for a right-tailed test, it's positive, right? Because it's going to be on the right side of that distribution. I could use that exact same, so when I think about, I have my critical value now, here's my rejection region. I could use the same process, but look up what's the value that would give me 0.05 and what's the value that give me 0.01 in that left tail. If I do that, I can get 1.65 and 2.33. So kind of here's my three rejection regions. Any questions up to that point? We're using the critical value approach here. So the next thing I need is my test statistic, which if we go back, the equation looks something like this. I can calculate the intermediate value, which is the standard deviation of my sample proportions, or I can just do it all at one time, which is what I'm going to have right here. Okay. So our sample proportion was 0.18. Our assumed true proportion comes from that null and alternative hypothesis, so 0.15 divided by the square root of 0.15 times 1 minus 0.15 over that sample size of 400. Okay. I think, if I remember right, this is 1.68 if we enter that into our calculator. So once I have my test statistic, the final step to make my rejection decision is, okay, does that fall in my rejection regions? Well, I plot, so if this critical value is 1.65, my test statistic of 1.68 would be right here. So it's in the rejection region at the 10 and 5% level, but it doesn't quite get past that critical value for the 1% level. So we would say that we can reject with 10 and 5% significance, but not reject, or we fail to reject at the 1% significance level. So essentially here I kind of did three hypothesis tests at the same time. Right? Once I had the critical value for each one of those different levels, it's just a matter of whether or not that test statistic falls in that rejection region, right? Or is more extreme or larger in absolute value than my critical values. Okay. Any questions on that before we keep moving? So here we said, you know, we can reject at the 10 and 5% levels, but we would fail to reject at that 1% significance level, right? Because my test statistic wasn't greater than, or wasn't more extreme, or wasn't in that rejection region for that critical value of 2.33, which corresponded to that 1% significance level. Okay. Okay with that?
Did you find that 2.33 again?
So I didn't go through the process. Remember how we looked up 1.29? You could use the same process to look up those next two alphas. So let's say I want 0.01 was the alpha that I wanted in my right tail. If I go to the table, there was two ways of doing that. I could look up 0.01. Oh, what's closest here? Looks like I'm in between these two values. So negative 2.32 and negative 2.33. So negative 2.33, but I'm dealing with a right-tailed test. So when I was looking up an alpha of 0.01, that was actually thinking about the area in the left tail. So it's that same value, but positive. Or similar to here, when alpha is 0.01, the area to the left would be 0.99. I could have looked up 0.99, and then I would have found the positive 2.33. Right? So it's kind of two different ways of looking up that critical value for your right-tailed test. Good question. Any other questions on that before we keep moving? So I'm going to use this same idea. So that test statistic we found was 1.68. Remember, the p-value is the probability I saw the test statistic I did or saw something that was even more standard deviations away from the null and went against the null hypothesis. So kind of here for a right-tailed test, my p-value is that probability I saw something past my test statistic, right? So I can look up that z-value, that test statistic. Remember, this is my z statistic or test statistic. If I look up 1.68, it'll tell me the area to the left. I wanted the area to the right, so I would have to do kind of 1 minus, right? So 1.68, I can look that up. Scroll down here. 1.68. So 0.9535. So the area to the left is 0.9535. So I wanted the area to the right. I subtract that from 1, and I get what? 0.0465. So now if I use my p-value here, 0.0465, I only reject if my p-value is less than alpha, right? That's my rejection decision. So is this less than 0.1? Yes, so I can reject at the 10% level. Is this less than 0.05? Yes, just slightly, so I can reject at the 5% level. Is it less than 0.01? No, so I'd fail to reject at the 1% significance level, right? Because 0.04 is not less than 0.01. And the only time I reject is if my p-value is less than alpha. And sure enough, those are the same 3 rejection decisions. Oh, I get this all on the, there we go. That I made before, right? I reject at the 10 and the 5% level, but I fail to reject at the 1% significance level. Okay. So we can use either approach, but will lead us to the same rejection decisions. Okay? So if I have a short answer question on the exam, and I just ask you, do you reject? You can use either one of these methods, right? Now, there's going to be some questions where I probably force you to do the critical value approach by asking you what the critical values are, asking you the test statistic. But either approach will lead to the correct decision. Okay? All right. So that kind of worked through that proportion example. And we kind of determined we only rejected the 5 and the 10% levels. So I've got some Excel stuff. I think I'm going to hold off on that for right now and kind of do that after we go through the next couple examples. So make sure how many we got here. Oh, okay. So let's see here. So just like confidence intervals, right? With hypothesis testing, we've worked through examples where we have a sample mean and we have a known population variance. Didn't seem very likely. We then also looked at examples where we have proportions. Those 2 situations, we always use the standard normal distribution, right? If I have a proportion example, standard normals or z-tables. If I have a sample mean, but I know the population variance, standard normal z-tables. The only time we start to use those student t-tables like we did for confidence intervals is if we only have a sample variance and we have a sample mean. Right? So what are the steps going to be to do hypothesis testing for that scenario? Well, same thing, identify the null alternative. We still need to know what alpha we're testing at, right? What confidence level or significance level. The kind of different step now is if I want to find critical values, remember before my critical values were coming from this standard normal or the z-tables. They represented z values. Now my critical values, I know that when I only have a sample variance or I don't know the population variance, I'm going to have to use the student t-table, so there'll be t values instead of z values. So I still find them the same way. There's still going to be the values that give me alpha in whatever tail I'm looking at, right? And it's still, right-tailed test, positive critical values, two-tailed test, negative critical values, two-tailed test, pairs of critical values, remember we said? So we'll make sure we do a two-tailed example here soon. But then the other thing that's going to be a little bit different is my test statistical equation. It looks exactly the same, other than instead of my population variance, I'm plugging my sample variance in there. That's the only thing that's different, right? So, once I plug the numbers in, my test statistic looks no different than it did before when I'm looking at sample mean examples. Now, just some kind of clarification. So this is still a test statistic, but I probably will now refer to this as a T statistic, right? So it's a test statistic coming from the student T distribution. Remember when we said a Z statistic, that's a test statistic coming from standard normal distribution, right? Or the Z tables. But other than that, once we have the critical value in the test statistic, we plot our critical values, draw our rejection region. If the test statistic's in our rejection region, we reject. We could do the p-value approach here as well. I likely, I shouldn't say likely. I would not ask you to find p-values on the exam kind of for when we only have a sample variance, and I'll show you why once we start working through some of these problems. Right? We still could do it, but for at least this exam, I wouldn't expect you to. So really the steps haven't changed. Steps haven't changed much. So let's say we want to test for whether or not the average home value in Muncie is different than 90,000. Okay? So right away we should know what type of tail test do we have here. Yeah, different than means not equal to, right? So what I'm trying to do, or what I'm trying to test for, I guess I should say, my alternative hypothesis, what I want to test for is that mean anything different than 90,000? So for my null, I assume the opposite is true, which is that it's equal to 90,000. So when you see this term different than, hopefully these are like easy null alternative hypothesis to identify. So we know we've got a two-tailed test. And just the other information that we're told, we find a sample mean of 85,000. I looked at 51 homes, and my sample variance is huge, so 100 million. Probably give you a number a little bit easier to deal with maybe on the exam than that. So we've got a two-tailed test. What are our critical values going to be? Okay. Well, what we're thinking about doing hasn't changed from the examples that we were looking at before. However, instead of a Z table or standard normal distribution, I'm looking at a student T distribution. So what I want, right, is a critical value, but here I have a two-tailed test, so it's going to be a pair of critical values that give me alpha total in the tails, or alpha over 2 in each tail. Okay? So let's, I think I asked for 3 different alphas, but let's just do the first one. So alpha of 0.1 over 2 is 0.005, not 0.005, 0.05, right? So I want 0.05 in each tail. When I ask you for 3 critical values, it's actually a little bit easier when we have a student T table distribution, because now, if I go, first of all, if I gave you a question like this in the exam, this is really kind. Why? I'm dealing with a two-tailed test here, so I know I've got pairs of critical values. D has to be the right answer. But how did I get these values, right? So even though we know D because of that very raw principle that for a two-tailed test, we have to have pairs of critical values. How did I get those? So if I go to my student T table, well, what I'm going to do is say, okay, look, what was my sample size? I think my sample size here is 51. So my degrees of freedom would be what? Degrees of freedom is simply n minus 1. So 51 minus 1 is 50. So if we wanted to do that ahead of time, we could have. So I've got my degrees of freedom of 50. The area that I want in the tails, right, alpha over 2. So I said 0.05, right? That was alpha over 2, 0.1 over 2. So I go down here to my degrees of freedom of 50, 1.676. The next one was an alpha of 0.05. Well, it's a two-tailed test, so it was alpha over 2, so 0.025. Go down to degrees of freedom 50, it's right there. And then the last alpha of 0.01, well, half of alpha is in each tail, so 0.005. Down at my degrees of freedom of 50, here's my critical value. So I've got, my critical values 1, 2, and 3 right here, right? Because I identified that degrees of freedom, and then it was just what area do I want in the tails, right? Now, it's a little bit trickier with a two-tailed test because when I say what area do I want in the tails, well, I want alpha total, but in each tail, right, I've got alpha over 2. So I had to look up alpha divided by 2 of those 3 different alpha values. So 0.1, 0.05, and 0.01, two-tailed test, divide those by 2, right? Because half of alpha is in each tail, so I need the values that give me half of alpha in each tail. So 0.05, you know, if I think about my alphas were 0.1, 0.05, and 0.01, well, I divided those by 2. That's the area I need to look up. I've got 0.05, 0.025, and 0.05. So those are the columns I looked at on the student T table at my degrees of freedom of 50, okay? Now, another thing, I think I mentioned this last class, but if we did have an example where we wanted to use the standard normal distribution, it's also kind of nice to use this. So before, like when you asked me earlier, how did you get the 2.33? Well, didn't show you, but then we went back and you have to use the standard normal table. But remember, this last row in the student T table, these are my standard normal distribution values. So I could have gotten that 1.28, 1.645, 2.326. Those are the same values as earlier, but they were all rounded to the second decimal, 1.29, 1.65, and 2.33. Right? So you could use this last row to kind of get even a more accurate value for that standard normal out to the third decimal. But for this example, we only had degrees of freedom of 50, not an infinite, right? Or we weren't using kind of a standard normal. So that's how we were grabbing these 3 values. Okay. Any questions on that before we keep going here? Yeah.
So you were looking at the alpha divided by 2 to grab those values?
Yep. So when I was looking up here, the column headings, and I said this when I first introduced the student T distribution, you can cross this alpha off if it confuses you. These column headings are simply telling you the area in the upper right tail. So you know that you have 2 tails, but you know that the area that you want in each of those tails is alpha over 2. So those were the values you looked up, 0.05, 0.025, and 0.00. Yep, you're looking up the area that's in each tail if you have a 2-tailed test. Yep, it's a good way of saying it. And then, of course, we had to go all the way down to what our degrees of freedom was. So, again, the tough part about these student T examples is that the critical values are going to be different depending on your degrees of freedom. Before, it was kind of nice. We were seeing the same 3 critical values all the time for left and right-tailed tests and for 2-tailed tests. Right? It's going to be always the same 3 when we're using that standard normal distribution. But when we use a student T, right, depending on the degrees of freedom, those critical values will change. Okay. All right, so we've got our kind of critical values there. What would the test statistic be? Okay. Well, if I look at this, I mean, the variance is kind of high, but seeing a test statistic like this would mean that I pretty much found a sample mean that was really, really close to the population mean, right? Because the test statistic, even if it's a T statistic, is still telling me something about the number of standard deviations away from the mean, okay? Well, the number of standard deviations being away from the mean is 0.002. That means I'm pretty much at the mean, right? I'm like almost no standard deviation. So I'm going to probably guess it's A or B here. And then one thing that you can kind of help you on the exam, I guess, with these multiple choice questions. So before we get too lost in what we're doing, if we just simply draw out, okay, well, what would the distribution of my sample means look like? I've assumed from my normal alternative hypothesis, right, that population mean is 90,000. So if what I assumed to be true was in fact true, my sample mean should be normally distributed around that. I then found a sample mean of 85,000. So when I think about converting this to my T statistic, right, I saw something below the mean, so I should have a negative test statistic, right? Because that test statistic is still a Z or a T value, and it's telling me how many standard deviations away from that assumed true mean I am. Well, if I see a sample mean below that assumed true mean, I'm going to be a certain number of standard deviations below or negative. Right? Now, how do I actually kind of find what the value is? So probably negative 3.57 would have been like the best guess there. If I want to like make sure that I can calculate this test statistic, it's just like before. Take the sample mean, you subtract the assumed true mean. It's just now we're dividing by the standard deviation of our sample means that is only using the sample variance, not a known population variance. All right? But from here, it's just what? 90K minus 85K over square root of, I think it was 100 million. And then my sample size was 51. So remember, when you're calculating your test statistic, you're not using degrees of freedom here, you're using your sample size. The degrees of freedom is only identifying, which of those distributions you're using when you're looking at things like critical values or p-values. So I think if we enter this into our calculator, we should get that negative 3.57. Okay. Any questions or anything up to that point? Now, we had those three critical values from earlier. We could have plotted them, but notice, so I've got positive and negative, these were my three different levels. My test statistic, if I draw this out, it's going to end up being in the rejection region because negative 3.57, right, is greater in absolute value than all three of these critical values, right? It's going to be kind of out way further in the tail and going to be in the rejection region at all these levels. All right, so for the sake of time, I'm not going to kind of draw out that again, but we'll work just more examples where I find the critical value and kind of plot those. But here, this one was a little bit easier to see. I mean, my critical values are at the most 2.68, and I found, or sorry, negative 2.68, and I found negative 3.57. That's going to be way further out into the tail or way more extreme. So I can clearly reject it all three levels here. Now, the critical value approach is usually how we're going to have to approach these problems because we run into a problem if I try to calculate the p-value. So remember, the p-value is the probability that I see something as far away as I did from the assumed true mean or even further that goes against the null. Well, here, remember, if we go back, we had a two-tailed test. So this actually only represents half the p-value. It would have been equally as likely for me to see something 3.57 standard deviations above the mean or further, right? So the other half of my p-value is in the other tail. So if I could find this area, I could then multiply it by 2, and that would give me my total p-value because I know that there's two tails of equal size. So I go to my standard normal table. I've got negative 3.57. I've got two issues. So one is that when I'm looking at the student t table, it's only looking at that right side of the distribution. So everything's positive. Well, I could actually recreate the exact same table and think about the left side of the distribution. All the numbers would be the same. It's just that they would all be negative because this is still a symmetric distribution. So I can still look up values here. Like let's say, I have what, negative 3.57. Well, I'm actually going to be looking for the test statistic of 3.57, right? Then I would kind of look and say, so for example, if my degrees of freedom was 32 and my test statistic was 1.309, the area to the right of 1.309 is 0.1, right? So I can look up my test statistic at this degrees of freedom and then find the corresponding area in the tail. The problem is if I go down to my degrees of freedom of 50, I don't see a 3.57, right? In fact, it only goes up to 2.678. So what's the area to the right of 3.57? Well, if the area to the right of 2.678 is 0.005, the area to the right of 3.57 is just going to be something smaller, right? So if I'm thinking about what I'm doing here, stop dropping my markers. When I look on that table's telling me that the area to the right of 2.6, I don't know if it was 5, it was 2.68 maybe. The area to the right of that was 0.005. Well, that means I know the area to the right of 3.57 has to be something smaller. But I don't know exactly what it is. All I can really say here is that the area in each one of these tails is less than 0.005. So the total area, right, if each tail is less than 0.005, if I add those together, I can say that the p-value is less than what, 0.005 plus 0.005, which is 0.01, right? But that's all I can say. And I can only put kind of bounds on my p-values. So that's why on this exam, and we'll kind of determine we can actually find, bound our p-value and still use that. And we'll do some more hypothesis testing after the exam. But for this exam, I won't ask you a p-value question where you only have the sample variance, because you're only going to be able to put bounds on it, and we haven't gotten a lot of practice with kind of this, so I don't want to throw another wrinkle in there. But this would be how you would do it. Right? But we can very easily do the critical value approach, right, which is what we did here, right? We found our critical values, we found our test statistic. We could plot that against our critical values and determine if we reject or fail to reject. Okay. Questions on that before we keep moving? I think I've got one more example that we'll work through by hand, and then I'll probably kind of show you some stuff in Excel. But at the same time as I'm doing Excel, I'll be doing it by hand as well, okay, to kind of hammer down this idea. So let's say now we've got this example where we want to test for whether or not the birth weight of babies born in Indiana is less than the national average of 3,287. Okay? So what we want to test for is our alternative hypothesis. So alternative hypothesis is this mean less than the national average of 3,287? We assume the opposite is true, which is that it's greater than or equal to 3,287. Okay. So what type of tail test do we have here? Well, we have a less than sign. So we've got a less than or a left-tailed test. Just some other thing we were told, the sample mean we found was then 3,132. Our sample size was 400 births, and our sample variance was some big number, right? So we just write that down, what we were given, just to make this easy. Well, we already identified the null alternative here. So we've got this left-tailed test. Right? What will the critical values be? Okay. So this one I'll plot out for us. So what I want to find, right, and I can start out with an alpha of 0.1. So I want to find the critical value for having 0.1 in my left tail, right? I've got a left tail test. So what's the critical value that gives me 0.1 in that tail? I would then kind of, I could think about, here's my rejection region. So what's my degrees of freedom here? Well, it's actually pretty large. And here's another one that kind of presents an issue for us. So I got degrees of freedom of 399. Well, if I go to that table and I try to find a degrees of freedom of 399, I got a problem, right? I start having big jumps here. I could do this in Excel, but my table is kind of limited, right? If I went up by 1 all the way up to 1,000, my table would be way too big, right? I couldn't even store it in my backpack or whatever. So if I've got 399, if I use the degrees of freedom that's closest to it here, we'll just assume that, that's going to be the closest. So we'll use 500. Well, then what I would do to find my critical value is, okay, at that degrees of freedom, I want 0.1 in that tail. So I scroll down, 0.1 in the tail at the closest degrees of freedom, 1.283. Now the issue is 1.283 is actually not my critical value, right? It's kind of, because our student t-table only looks at the right side of the distribution, if I want to look at the left side of the distribution, it'll give me the value, right? 1.283 is the right value. It's just that for a left-tailed test, my critical values are negative. So when it comes to using the student t-table, you can use it to find the values, but then you're really going to have to remember that depending on what type of tailed test I have, if it's a left-tailed test, it's that value, but negative. Okay? Right-tailed tests are a little bit easier using the student t because it's looking at the right side of the distribution. We could then do the same thing. What's the critical values that give me 0.05 and 0.01 in those left tails? Well, when I was on that table, it would have actually been pretty easy. I want 0.1, 0.05, and 0.01. Those are my three alphas. That's the area I want in the tail. So I go down here. It's going to be 1.283, 1.648. Remember, I have to make them negative because I'm looking at the other side of the distribution. And then 2.334, so negative 2.334. Okay. But now I've got all three of my critical values, and I can think about, there's my rejection regions. Okay. Does that make any questions on that? Yeah. So you don't have to if you don't want to. We said, okay, so good question. I'll answer here in a second. Any other questions for, yeah.
What does it mean that they're negative? Because you said you have to remember on the left side when you do a left tail test, it's going to be negative, but what does that mean or signify?
So remember, these values represent the only evidence. So it's like saying, if I see sample evidence that's more than 1.28 standard deviations below what I assume to be true, then I can reject, then I'm okay rejecting. So the problem is with a left-tailed test, the only evidence that goes against the null is evidence on the left. So I'm going to have to set my threshold to be a certain number of standard deviations below or negative critical values. Okay. Whereas on a right-tailed test, only evidence on the right side or above a certain value, I could reject the null. And so there I have to be a certain number of standard deviations above that assumed true mean when I'm setting my threshold.
Okay, that makes sense.
Yep. Okay, good questions. So I'm going to calculate my test statistic. I'm not going to write the whole equation out again. I'll show you on the formula sheet here in a second where this is at. But, we have the format here, and I put Z. That was wrong, right? We only have a sample variance, so I'm using a student T table, so I have a T statistic. So I've got my sample mean minus my assumed true mean. So I go up here, got those values there. So 3132 minus 3287. And then I'll divide by the square root of my sample variance divided by my sample size. So 439,907 over 400. So that will give me my test statistic. Yeah. It's okay. 390. Oh, up here. So the way so our degrees of freedom is helping us identify what student T distribution we should be using, because there's truly every single different sample size has its own student T distribution. The reason why we do degrees of freedom, so think about it this way, we can't have a degrees of freedom, we can't have like you could replace degrees of freedom here and simply do this as the sample size, and it would just start at 2. Because if you go lower than a sample size of 2, you've just grabbed one observation, you're back to just the distribution of the data. So it relates to some things that if we were to kind of continue, we'll talk about it once we get to regression, but degrees of freedom start to become more complicated when we start to develop more complicated statistics. And so we'll start using the terminology here, and it makes a little more sense once we get to something like linear regression. But the idea was that we've got a sample variance, so dividing by n-1 is going to influence how much our student T distribution varies from the standard normal. Because when n is large, dividing by 1,000 instead of 1,001 isn't that much different than, isn't that much different, but dividing by 3 instead of 4 can make a much larger difference. Yep. All right, so I have to check here because I can't remember what this works out to be. So we get our test statistic, it's negative 4.7, we'll call it, just to make it kind of easier to write. So approximately negative 4.7. Well, this is kind of an easy one because where would that be? Somewhere way over here, right? Negative 4.7 is going to be way, way out here, which will clearly be in the rejection region at every single level, or at every single level, 10, 5, and 1%. Okay, so when I start seeing test statistics that are over 3, I should start to be thinking, okay, my rejection decision is going to be reject. It doesn't matter what alpha I'm looking at, my critical values never kind of get out as far as 3. If I'm more than 3 standard deviations away from what I assume to be true, then it's probably not the true mean, right? So that was a scenario we had here where we had a pretty extreme test statistic. Okay. What would the p-value be close to for this, if you had to guess? There's a certain value that it's going to be really close to. If the area to the left of negative 2.33 is 0.01, what do you think the area to the left of negative 4.7 is going to almost be?
Zero.
Really close to 0. So if I asked you for, not going to do this on the upcoming exam, but I asked you for the p-value here, and one of the answers was approximately 0, you should be able to determine that from kind of thinking about what that test statistic would mean relative to these critical values. Okay. I wanted to say something else here. Now I forget what it was as we were talking. What did you asked me a question and I said I'd come back to it. Oh yes, yeah, thank you. So the only reason I put these arrows is to make the visual easier to see that the test statistic is clearly in that rejection region. You don't have to draw the arrows. In fact, one of the other ways that you can actually do the critical value approach, if you don't want to draw it out, I think it helps to draw it out. But we're always really looking to see, is the absolute value of my critical value, if that's less than the absolute value of my test statistic here, a t statistic, then I reject, right? And the reason why we do the absolute value is so that we can always use this, so that it works for a right-tailed test, or when we take the absolute value, it gets rid of my negative signs. It would also work for a left-tailed test or even a two-tailed test. So here you kind of can see, I mean, negative 4.7 is larger in magnitude than negative 2.33. So when I take those absolute values, this would hold and I'd reject. Or if I have it drawn out and I just plot the points, I can clearly see it's in that rejection region. So that's the only reason I do it, is just to kind of have a visual that lines up with what we're doing to make it a little bit easier. Yeah, like if I never drew these out for you, which I don't really have to do, it just told you, just remember this. I don't know, to me, it just makes it a little bit harder. Well, now I've got one more formula I got to remember, it's checking, and if I just draw it out, it's pretty easy to see that it's larger in absolute value, right? It's kind of more to the left here, or it's more to the right for a right-tailed test. So it's just a tool for thinking about these better and making sure you're kind of getting to the right answer. All right, any other questions on this before I kind of go back? Okay, so I kind of have a reminder, just synopsis slide of the steps for the p-value in both the critical value approach. I've got some extra questions here. I'll probably save these and work through some of these on Tuesday. Remember, the exam will be open next Tuesday and Wednesday, but I think seeing some of this in Excel could help. So I've got a hypothesis testing blank file up on Canvas. After we work through some of this stuff today, I'll actually think, I might have actually put this up there yesterday just so I didn't forget. Let's see. Hypothesis, yeah, I did put up the complete version as well. So we'll kind of have what we worked through today, but there's a completed version of this as well. Yeah.
So it's open next Tuesday, Wednesday?
Yep.
We're not going to do a review like we did last exam?
So we don't have as much time to do review this time. Now, kind of what I'm going to be doing right now with Excel, because I'm not expecting Excel in there, we're just going to be going through more hypothesis testing problems. But Tuesday I'll do review as well. So I would suggest not taking it Tuesday before class, because Tuesday we will just be doing review. I'm trying to get some videos filmed, but my office hours have been more full this week than I expected. I'll get a couple up there tonight and hopefully a couple more tomorrow, such that you can see me working through the entire practice exam. But one thing for this exam, both the practice exam answers that I posted has formulas of how I worked it out. So it's not just kind of what the answers were. You do have you can kind of see what the work would look like. I'll get some videos up there if you want some additional stuff where I'm drawing a few more things to kind of help get the concepts through as well. Yep.
So is there no possibility for a Thursday, Friday test?
No. Yeah, well, if we do that, I'm gonna start making the final kind of a beast for you. So it will be next Tuesday, Wednesday. Yeah, where we'll just get kind of 1 day of review in there. Yeah. And I'll be doing some review in my class on Monday, my classes on Monday. So I'll be getting some videos of different exams. I'll probably work through different exams for both classes. That way I'm just getting more videos up there of me working through different problems. All right. Oh, this is on the in-class data folder. So I'm going to work off this hypothesis testing blank one. So it's under files and then the in-class data. So we'll just go to a proportion one first. Make this one a little bit trickier. So I'm going to delete what I've got here. Delete this, and I don't think this was originally in the folder. Yeah, I think it's just something like this, right? So I think originally I also had the sample size in here as 100, and this was 0.25. So at least we kind of see where we're going. So if I've got a 1-0 variable, and if you haven't finished the Excel assignment yet, I feel bad for you, but you know, a lot of you have reached out. When we were dealing with proportion examples, if I have a 1-0 variable, how do you find the sample proportion? It's simply finding the mean. Because what that means is going to do is it's going to add all these up, but the zeros don't do anything, so it just adds up the number of people here who ever tried an e-cigarette. And then it divides it by the total number of observations. Well, that's how you find a sample proportion. This many people out of this many people reported that they've tried an e-cigarette. So this was like some youth data, like high school, middle school kind of age students. They did this huge survey. Now, I said assume the sample size to begin because it's a really large data set. We're going to start out assuming it's 100, and I'll kind of play around with this to kind of get at another concept as well once we kind of complete this. So really what we're doing here is we've got our sample proportion. We've got our hypothesized true value. So I'm going to make this one a two-tailed test. So we're thinking about what we're trying to test against, or test for, I should say, is that this proportion, right, is not equal to 0.25. So we assume the opposite is true for our null, okay? So the next thing we do, and actually, oh, did I drag and drop this? I think it's on my desktop. So what I'll do here, just pull this up real quick, just so I can start kind of getting a little bit ahead of it where I can tell you where to find these things on your formula sheet. So if you go down here, we've got our 3 test statistic equations. Okay? So here's one where we've got a sample mean and we got a population variance, sample mean, only a sample variance, and here's our proportion example. So we can use this equation, right? I think if we go back to that Excel file, we found it's approximately 0.34 was the sample proportion we found, and we were using a sample size of 100. Right? Well, really, at this point, I've got 0.25, 0.25, 0.25, 0.34, 100. I've got everything I need to plug into this equation. Or what I can do is just use Excel to be my calculator. So if I looked at Excel, right? Okay, make sure you guys can see what I'm seeing. All I'm going to do in that numerator is take my sample proportion minus that assumed true proportion. Right? I'm then going to divide by the square root of that assumed true proportion times 1 minus that assumed true proportion divided by my sample size, right? So all I was really doing there was putting into Excel that equation that I knew would give me my Z statistic or my test statistic. Right? It was just that equation I pulled from the formula sheet. But instead of typing these values into a calculator, I can literally just click on the cells that those numbers are in. So that should give me my test statistic. So there, it's just using Excel to be a calculator. At the next point, how could I find my p-value? Well, here I've got, see if I can get this to show. There we go. So I've got my Z statistic, right? I'm dealing with proportions, so I know I can use that standard normal distribution. I just found 2.02. So I want the area that's more extreme than that. However, I've got a two-tailed test, remember? So it's going to be this area times 2. So this gets a little trickier in Excel because the only formula I have that I can use is the norm.s.dist. So I'm using the standard normal distribution. Here's the z value, my z statistic, comma 1. So the way that this worked, it was similar to the table. It only tells me the area to the left. However, I want the area in that upper right tail, and then I want to multiply it by 2. So what can I do? Well, if I subtract the area to the left from 1, that would give me the area over here in this right tail. Right? So you can kind of think about when I'm using that norm dist function, sorry, norm.s.dist, it's telling me the area to the left of 2.02. I want the area to the right, so I had to subtract that from 1. And then it's a two-tailed test, right? So I know that seeing evidence on this side, it was equally as likely I had seen evidence on the other side. So I need to then, final step, multiply it by 2. Okay? Any questions on that? Like I said, I'm not going to expect you to use this on the exam per se, but it might help kind of start connecting some things we did before with what we're doing currently. So there's my p-value. At this point, kind of a neat little thing, I mean, little trick I guess you can do, is we talked about that if statement before. Well, my rejection decision is always the same. It is my p-value less than alpha, right? So I had my alpha up here in a cell, comma, if that's true, just put in the word reject, right? Because that's what I should be doing. Comma, if that's false, put in the words fail to reject. Right? So here it's very clear, it's easy to see, okay, 0.04 is not less than 0.01, so hopefully when I hit enter here, sure enough, it puts in the words fail to reject. But if I want to do my test at the 5% significance level, where alpha is 0.05, now my p-value is less than alpha. Hopefully this should change. Sure enough, right? I've got my rejection decision built into that if statement, and I can kind of display the word for what I should be doing here. Any questions on any of that? Keep continuing here. So how can I find my critical values? Well, remember, what I was doing with my critical values, do I have an example of a, where's the one we were doing earlier where we had a two-tailed test? Here we go. So for a two-tailed test, I'm trying to find the values such that I have alpha over 2 in each tail. So what I can do is I can work in reverse. I know the area in the tail. I want to find the z, or in this case it was a t value, but now we're dealing with one where we have the standard normal distribution. We want to look up that z value that gives us alpha over 2. So we're working in reverse or norm.s.inv, the kind of the inverse. Right? So I tell it what area do I want in the tail here? Alpha divided by 2. Now for a two-tailed test, I have pairs of critical values. This is going to give me the negative. So I could the way I kind of like to see this in Excel, you can indicate this by inserting a symbol and, making sure that it shows positive and negative 1.95996. Or I can just take the absolute value right next to it to kind of show that I have two critical values here. Now, if I really wanted to, I could plot those critical values. So, negative 1.5. So, negative 1.959, whatever, and then positive 1.959. So here's kind of my rejection region at the 5% level. I then have my test statistic of 2.02. So here I would say that I reject, right? Which, sure enough, the p-value approach led me to that decision as well. Right? Now, if I change my alpha to like 0.01, well, now notice my critical values would be all the way out here at what, 2.57 and negative 2.57. Now, my test statistic isn't in my rejection region, so I'd fail to reject. Okay. So this is kind of was my alpha of 0.01, and this was the alpha of 0.05. Okay. Any questions on anything there, or do you want to see something in that Excel, some more, a cell again, or a question how I did something? Yep. So that's where this one was a little tricky, because we can use that norm.s.dist function to find the area to the left. So where was that? Oh, here. Oh, okay. Yeah, so we wanted the area to the right, so I could find the area to the left of my test statistic. Subtract it from 1, that would give me the area to the right, and then multiply it by 2 because it's a two-tailed test. Okay. Yep.
So you need the critical values to be able to reject on a certain level, or on a certain,
You need,
like alpha.
yes. Yeah, you'd have to, like, for every alpha, you have to find what critical values correspond to that. That's why the p-value, like, to me, the p-value is a little bit easier, because once I have the p-value, I can very quickly tell you all the levels I can reject at and all the levels I fail, right? Anything above 0.042563 here, I can reject those alpha values. Anything below it, I fail to reject. With a critical value, it's not as easy, right? But with a critical value, what you can actually think about is your test statistic is like any critical values past this, I'd fail to reject. Any critical values kind of smaller than this, I would be able to reject. But it's not as easy because I don't like know what those critical values what critical values correspond to which alpha values. So it's a little bit, the critical value approach is a little bit trickier. The p-value I always think is a little bit easier. All right. So we're okay. Any more questions at this point? I'm going to try to kind of walk us through something here. Okay. So I've got this rejection decision. I'm failing to reject at the 1% significance level, and alpha is 0.01. What if instead I don't use 100, but I actually use the correct sample size, which is, using that count function to count the number of observations. Here, I got to move this here so I can scroll up fast. Okay. So when I hit enter here, it's going to put in the actual sample size. So I originally had the sample size as 100 for a reason, because it was a more interesting test statistic, and the p-value, I could reject some levels but not others. If I hit enter here, what's going to happen? Well, remember, this is the standard deviation of my sample proportions here in my denominator. So if I increase my sample size, right, that was the idea. If I take larger samples, I'm going to kind of reduce the variation I see in those sample proportions or my sample means. So when I increase my sample size, this standard deviation of my sample proportions goes down. And if my denominator is smaller here, that gives my test statistic higher, right? Because higher sample size, smaller standard deviation. So being the same distance away is now going to be a higher number of standard deviations away. Well, that's the definition of our z-values, our z-statistics. If my test statistic is greater, what's going to happen to my p-value? It's going to be smaller, right? So I can kind of see my p-value should be smaller, where if I make my rejection decision based off of this p-value less than alpha, well, if my p-value is getting smaller, it's more likely that I can reject at certain levels. So we'll see if that plays out. So sure enough, my test statistic gets higher, right? My p-value now is lower. In fact, it's almost 0, right? And I'm much more likely to reject at any alpha. I could go all the way down to like 0.0001, and I'm still rejecting, right? And the reason why is we went from 100 to 18,000 observations, right? We just have a lot more information about where that true population kind of or proportion might lie. One thing you could have done here is calculate this intermediate step when you were doing your test statistic. So proportions, yeah. So I could have done the square root of my assumed true proportion times 1 minus the assumed true proportion divided by my sample size. I could have done that over here in a cell. And then my test statistic equation becomes a little easier because instead of having to reproduce that, well, I already did that ahead of time. That's over in this cell over here. Okay. So I get the same test statistic. It's just breaking it up into 2 parts. But it allows me to see something like when I had a sample size of 100, here was the standard deviation of my sample proportions. When I go to my actual sample size, right, 18,000, that drove that standard deviation down a lot. So then being, the same distance away from the assumed true value, it's going to be a much higher number of standard deviations. It was like what, 2 compared to being 27, almost 28 standard deviations away. And you know, once I have this high sample size, like I can really I could probably reject 0.32, right, as the true proportion, even though what I found is pretty close to that. I might even be able to reject 0.33. Yeah, I actually not at the 1% significance level, but I think at the 5 I actually could, right? And you know, my sample proportion is barely any different from that assumed true value. But it's because I have such a large sample size, I can really kind of laser down where that, you know, values for what that true population proportion should be, or could be. I shouldn't say should be, could be. Okay. All right, I'm going to show you, we'll go through one more here. I've got one more thing I want to show before we get out of here. So I had some other data on this, which was like the age, the first age they tried an e-cigarette. Some of these kids were getting started pretty young. Got a 9 in there. So I'm going to say, can I test for whether or not the true difference is well, let's not do a two-tailed test here. Let's do a right-tailed test. Okay. So is it greater than 14.3? Right? So what I'm thinking about here is the hypothesis test that I want to do is that mean greater than 14.3? Actually, I don't want to do that because, hold on, let's choose a different value. Let's just do 14. And then less than or equal to 14. So I'm going to change this from 14.3 to 14. Okay. So I've got a right-tailed test here. My test statistic, if I go to that formula sheet, did I close it? Did I have it pulled out? Here, I had it. So it's still, here's my test statistic equations. Well, I have a sample mean and I only have a sample variance, right? If I'm looking at this, I only have my sample variance here. I wasn't given a population variance and I don't have population data. So really it's just using Excel to be a calculator, right? I'm going to take the sample statistic I found, the sample mean, minus the assumed true mean, and then divide that by the square root of my sample variance divided by my sample size. All I did there was use Excel to be my calculator and get this formula. I clicked on all the values that were, you know, the different variables in this formula. Okay. So that should give me my test statistic. It's a pretty large test statistic here, but we'll kind of continue through this example regardless. So what should our p-value be close to here? If my test statistic is 8.22, what's the area to the right of that going to be close to? More like, so if we look at kind of my t-tables, right? You know, if I'm thinking about values of 2 and 3, the area to the right of them is 0.005. Well, if I've got a test statistic of 8.22, that's way far into the tail. The area to the right of it's going to be pretty close to 0. Okay? But before we said all we could do is put a bounds on it if we had to physically use that student t-distribution table. Okay? So now, how can I use Excel to find the p-value? Well, for the normal distribution, we use that norm.s.dist. For student t-distribution, we can use the t.dist. Okay? We tell it what value do you want to use for that t-value or that test statistic, comma, what are your degrees of freedom? Well, here I've got my sample size, and my degrees of freedom is that minus 1. And then, do you want to make it cumulative? We're always going to put a 1 there, so we're always looking at the left side of the distribution. So this is going to tell me the area to the left of 8.22. Well, I don't want the area to the left. I've got a right-tailed test, right? So if I'm thinking about what I'm doing here to kind of give us a visual as I'm working through this in Excel. We found what, 8.22, I think. Our p-value is the area to the right of that. The t.dist function will tell us the area to the left. So to get the area to the right, we need to subtract that from 1. Right? So here, you go 1 minus, and this is pretty much approximately 0. Right? So this, again, shows the power of having a large sample size. Even though my sample mean I found isn't that much different from the assumed true value of 14, right? It's you know, the standard deviation is being driven down so much by this high sample size that even though I'm only 0.2 away, that's a high number of standard deviations. That's 8 standard deviations away. So then I get a p-value of approximately 0. I could set up my rejection decision the same way I did before. So I can use that if statement, say if my p-value is less than alpha, comma, put in the word reject, comma, if it's not, put in the word fail to reject, right? The exact same thing that I had in the other worksheet. Okay? That's just that decision. Like burn that into your memory. If the p-value is less than alpha, we can reject. So clearly we can see this p-value is going to be less than any alpha, so we should always be seeing reject here no matter, you know, what, oops, I put it in the right cell. No matter what alpha that we're kind of looking at. In fact, I could probably go pretty low here. Yeah, I can still reject it. I probably reject it even 0.001. Yeah, so we can reject at any level. So if we want to do the critical value approach, before we're working in reverse or inverse. We know the area we want in the tail. So before we use norm.s.inv, well now we're using the student t distribution, so just t.inv. This was similar to how we found those t values for confidence intervals when we were building a confidence interval for a sample mean where we only have the sample variance. I said we're actually building the confidence interval for where the population mean is, but sorry, using the sample mean. So we only have a sample variance here, so we got to use the student t. The area I want is going to be alpha, right? That's the total area I want in the tail, comma, my sample size minus 1 is my degrees of freedom. Now the issue with this is, just like the norm.s.inv, t.inv is going to look up the area in the left tail. So it's going to look up 0.01 in your left tail, right? So it's going to give you your critical value, but it's going to be negative, right? In fact, the only thing that we can, you can kind of change, you could just put the absolute value around this, and now you're guaranteed that, well, it's a right-tailed test. I know that the t-value that gives me alpha in the lower left tail is the same as the t-value that gives me alpha in the upper right tail, but positive, right? Positive for the right-tailed test. So I can use the absolute value function here. Now I get my critical value for this right-tailed test. And one thing I kind of want to point out here, if I use my norm.s.inv, and I do the same thing, I look at alpha, and then I take the absolute value. Okay. Notice these are almost the same, because we said as the sample size gets higher and higher, the student t and the standard normal distribution start getting closer and closer to each other. So here with such a high sample size, using the standard normal is a pretty good approximation for what that student t distribution is, right? We're only off to the fourth decimal point. Okay? But that's how we can kind of use, right? It's the same kind of thing we were doing, just instead of norm.s.dis and norm.s.inv, dis and t.inv. Okay? Oh, sorry. Yeah.
I thought I understood, but I just got a little confused. The absolute, when you use the absolute function instead of doing the 1 minus, I know with the right side that you usually do 1 minus t-dist or t-inv.
Oh, so if we were doing the p-value, right, that's where we had to do the 1 minus, right? Because there we're dealing with the areas kind of on each side of this value. We're looking at critical values, right? We're always going to have to tell Excel the area that's in the left here. So instead of using the absolute value function, what could I have done? Well, I know that I wanted an alpha, so with the critical values, I know I wanted an alpha of 0.01 in this upper right tail, and I'm trying to find the critical value that gives that to me. Well, I said you could just put in alpha, and then that's the right value, but for it's a right tail test, so make it positive, just take the absolute value. I could have also looked up the area to the left here, so 1 minus 0.01, or 1 minus alpha. So let's say I get rid of this absolute value. I could have said the area I want to the left is 1 minus alpha, right?
It's the same thing.
Same exact thing. Yep. It just kind of depends on how your brain works. Like for me, it's easier to just look up alpha and then remember the rule that right-tailed test, it's that value but positive, left-tailed test, it's negative. But if the visual kind of makes more sense to you and you know, I'm always looking for the area to the left, so the area to the left of this critical value should be 0.99, you know, then you can do it that way. Right? Any other questions at this point? All right, we got 4 minutes. I wanted to show you something, but I'm worried I'm going to run out of time. I'll go through it pretty quickly, right, just to kind of give you a good idea of what's going on. So we talked a little bit about type 1 errors. So I did this thing where I had population data on tuition amounts from schools. So here's this tuition variable. I know what the true mean is. I can calculate that because I have the population data. So I assumed that the mean was equal to that value, right? So I know that my assumption is true. I kind of cheated, right? Well, I know that if what I assume to be true is in fact true, my alpha should be the proportion of type 1 errors I make. What was a type 1 error? It's the proportion of times I reject the null, that the true value is equal to what the true value is, when in fact, I reject it when I in fact shouldn't have, right? Because what I assume to be true is in fact true. So I can force that here. I then created like these random numbers and then took a random sample, right? So this matched up a random number to the school ID and then put their tuition amount in here. So I've got right here my first sample, random sample of size 50. I can calculate my sample mean, sample variance. I could then calculate a test statistic. I could then calculate my p-value. Here I did a two-tailed test. Notice I'm multiplying by 2. And then see if I, if I reject or not. So this was kind of the idea. If my p-value for this sample is less than alpha, I can reject. If it's not, I fail to reject. So notice here, like, I think I have alpha set at 0.01. So none of these, I'm not going to be rejecting at any of these levels. But here, this is less than 0.01, so I would reject. So what I then did was add all those up. That should give me the number of times out of these 1,000 different random samples that I rejected when I in fact shouldn't have been. So the number of times I rejected out of 1,000, notice 0.097. And that's what happens when I have myself alpha set to 0.1, right? So the number of, or the proportion of type 1 errors I'm making is pretty much alpha, or whatever I set my alpha at. Now this changes a little bit because it randomly generates new numbers, but it's always floating around 0.1 here, right? And if I change my alpha, right, to 0.01, and now it redoes all these hypothesis tests for these 1,000 different samples, right? Well, now I start to get the proportion of the times I rejected when I shouldn't have been, floats right around 0.01. A little bit higher sometimes, a little bit lower sometimes. And that's because I only have 1,000 samples. To get this to be exactly alpha, I need like an infinite number. It's kind of what I did when I showed you the confidence interval example. So you can prove this stuff to yourself, kind of using this data and generating these random samples. So I don't know. I thought that was kind of interesting, might kind of help kind of the thought process of what we're doing here. Before we get out, because we're running out of time, I wanted to mention a couple things about the exam. So it will be next Tuesday and Wednesday, open all day. Once you get on, you'll have 90 minutes to complete it. So it's going to have 18 multiple choice questions going all the way back to uniform distribution. So some of that uniform distribution, if you review the practice exams, hopefully those are some easy points, the first couple questions. And then one kind of larger short answer. I believe it has like 6 parts to it. Some parts harder than others, but it's going to be, I'll kind of let you know ahead of time, it's going to be a hypothesis testing thing. So I know that that's the newest thing we worked on. That's going to be hard. So I want to give you an opportunity that there's a part where even if you don't get the answers perfectly correct, I can give a lot more partial credit on that short answer if you show as much work as possible, okay? I can't reiterate that enough. I'll probably, I'll mention it again on Tuesday, but show as much work as possible there, because I'm really trying to kind of give some partial credit, because I know that hypothesis testing, it's the newest thing that we've done. And by no means do I think you're going to have like the perfect understanding of it. We're still going to kind of work on some hypothesis testing after this exam. But I am going to kind of use the exam to see where we're, evaluate where we're at with our understanding up to this point. Okay.
Does that have to be done in Excel?
No. You can do it on Word. You can take pictures of you working out by hand, just like before. It doesn't have to be done in Excel. It can be, doesn't have to be.
Did you say the practice exam is like an accurate representation of the exam?
Yep, other than no short answer. But you can kind of turn some of those questions into a short answer, and that's what you would kind of expect to see on the exam. Yep, so study those practice exams. We'll review one of them on Tuesday. I'll be posting some videos today and tomorrow of me reviewing parts of those practice exams as well. And if you have any questions, please feel free to reach out to me. I'll go over, once again, the specifics of the exam again on Tuesday. Other than that, try to enjoy your weekend, and I'll see you next week on Tuesday.